ladies and gentlemen, today's class recording has started. So, on Tuesday of last week, we finished up this evolution of the atomic model, right? And we talked about the differences going all the way, starting at Dalton's atomic theory, and then bringing it all the way back down to Schrodinger's model. One of the key features of Schrodinger's model is the development of what we refer to as atomic orbitals. What is an orbital? What is an orbital? Ronnie, go ahead. A place where we are most likely to find electrons, right? There are several orbitals that show up, right? But what we do with this section is start trying to distinguish one from the other. But by general definition, an orbital is a place where electrons are likely to show up. Okay? Remember Schrodinger's model, right? All of these black dots in here represents locations where electrons were at some time in the past. And if we look at where they were, we find out that there are certain areas that are darker than other areas, meaning that those electrons were there more often, and therefore we can now make a prediction that that's where they will be in the future. Are we guaranteed to find electrons there? No, the possibility exists that they could not be there. They could be where? Anywhere. They could be on the moon, right? Is it likely? No. Is it possible? Yes. Okay? All right. So we started off drawing this picture, right? And then if you guys remember, on Wednesday, I sort of made mine a little bit more. I made it with the graphics on the computer. Not that they're great, but they're a little bit clearer than some of this. So this was the first orbital that we drew, right? First, where's the nucleus on this drawing? The origin of this XY axis, right? Remember, nucleus is very small compared to the rest of the atom. So this is the first orbital that we drew. What can you tell me about electrons that are in this orbital? Nothing good. Low amount of energy, right? Because they're very close to the nucleus. But we then said there's kind of a consequence of that. That yes, this orbital, electrons that are in it have low energy. But the consequence is, are there a lot of electrons in that orbital? No. Why not? They're attracted to the nucleus, but they repel each other, right? So while electrons want to be here, not too many of them fit in that spot because they start repelling each other, right? Okay. Next orbital we drew looked like this, right? So we said it's another sphere, okay, but we changed colors. That sphere is hollow. It goes around the outside of the one that we drew previously, right? But then we said, as we start moving farther away from the nucleus, there's a little more space. And so now we begin this sort of tension between where can electrons go to get as close as they can to the nucleus, but still trying to stay away from all the other electrons, right? So the next thing that we added looked like this. Jafar, go ahead. The electrons that are in the red, let's go here. Electrons that are in that red orbital, that hollow sphere, have more energy than the electrons that would be in the yellow orbital, okay? Because we're farther away from the nucleus. So, Jafar, even though Bohr's idea of a ladder isn't true, his idea of quantization, that the farther you away, the location of the electron relates to its energy, and the farther away from the nucleus you get, the more energy those electrons have, that part still is what we believe that to be true, okay? Ronnie, go ahead. They are not overlapping. The spheres are more like hollow. So we kind of said, like, Ronnie, you know, like those like Russian stacking dolls that have like that one little one, and then like a smaller one goes on the outside, and the next one goes on the outside. It's kind of like that, where you have the yellow one in the middle that surrounds that space around the nucleus, but then the red sphere goes around it. Okay, does that make sense? But then we said that as we get farther out from the nucleus and we get more space, we can, like I said, start settling into those spaces of, are we close to the nucleus but still far away from other electrons? And then we start adding in other orbitals. And we said that this is actually 2 orbitals, right? You have one that looks like this and one that looks like this. Okay? So now, Ronnie, building off that question that you just asked, the reason why I made this sort of look the way that it does, the lines that connect the 2 like bulby parts on the end, they're very skinny because they're crowding into the space that already has electrons. You know what I'm saying? So if we look at this as an orbital altogether, we won't find a whole lot of electrons in this space, or we won't be likely to find electrons in this skinny part. We'd be much more likely to find them on the outside because now they're away from the other electrons that are there. Okay? This is actually 1 orbital, okay? The whole figure 8 shape is 1 space, okay? It's not the same shape as this one, but it is 1 space, okay? That'll make sense as we go a little bit, Steve, hopefully that'll make sense as we go a little bit farther along today, okay? We'll get into that a little more, okay? Pat, go ahead. Yep. Those are 2 separate orbitals, okay? So this is a separate orbital. This is a separate orbital, and we also said that there was a 3rd figure 8. Do we remember the 3rd figure 8? We said the 3rd figure 8 actually goes which way? Z-axis, right? So we have an x-axis one, we have a y-axis one, and then we also have a z-axis. Each one of those figure 8s is a separate orbital. So there are 3 of these red figure 8s that show up just outside the red sphere. Okay? Jules, go ahead. Yep. It's hard to draw the 3rd one on this picture without your picture getting really, really complicated. You know what I'm saying? Like, there are some ways that you can kind of represent 3-dimensional things 2-dimensionally. You know, we kind of draw them diagonal-ish and stuff like that. But I would rather at this point you just kind of understand that I can draw the X and the Y one, but the Z one I just kind of have to imagine it's there. Right? And we said that's one of the things that's tough about this sometimes, is that we're trying to represent a 3-dimensional situation 2-dimensionally, so we have to picture a little bit in our head what's going on. Okay? All right, good there. Okay. The next one we drew looked like this. Okay? So, similarities, differences, right? First, difference being what? That's blue, right? That's the difference I wanted you, right? So, difference being that it's blue, all right? But, similarity, right? Every time we start a new color, what's the first thing that we draw? Sphere. A sphere, right? Now, how is this sphere different than the other spheres, Stephen? Let's do energy first. Electrons in this higher energy than any of the other orbitals that we've drawn. Okay? Then, next thing we added were the figure 8s. But now we got blue figure 8s, right? But then we also said when we got to the 3rd, the blue level, we added a new shape, right? We added this butterfly shape, okay? Which, if you isolate it from all the rest of them, looks like this, okay? So, Pat, again, this is all 1 orbital, okay? I know that seems weird in that, well, wait a second. How would 1 electron fit in that 1 space? It's really kind of a weird shape. But that's, if we look at those areas, that's where we're likely to find electrons. Not in all 4 of these lobes, but maybe in 1 of those lobes at a time, okay? And then, Ronnie, just kind of going back to something you brought up before, again, I'm trying to connect these butterfly wings, right, with the skinny part in the middle. We're not real likely to find electrons in this area here because now we're overlapping all those other orbitals that are already there. We're much more likely to find them out in this area out here. Okay? So we ended up with this, right? Okay? And then I think, did we do the fourth one or no? Or did we get it on Wednesday? Anyway, even if we didn't, you don't necessarily have to draw the fourth one, okay? Oh, by the way, I'll mention this too. When we finish this, I will make PDFs out of all these things that I write up on the board, so you'll have my representation of it up on the board too. You might find that a little bit clearer to follow because each of my pictures is a different slide, whereas yours are all kind of piled on top of each other. So I'll make that available. Not that that means that you shouldn't write anything down for the next couple of days, but just so you know, it will be waiting for you eventually, okay? But then we said the next one we added looked like this, right? Similarities, differences, right? Difference,
Different color.
bigger, and different color, right? More energy than all of them. But similarity, new color, what's the first thing we draw?
Sphere.
Sphere, right?
Hollow.
Hollow sphere, right? And then the next thing that we would draw? After spheres, what shape shows up next?
The butterfly.
Nope. Figure eight's next, right? And then butterfly. Okay. So, do you draw this? If you want to, yes, although it's more important that you understand the pattern as opposed to have the picture. Does that make sense? So if you get that it goes sphere, then figure eight, then butterfly, that's good enough for now. Okay? Stephen, go ahead.
Is there ever going to be where there's going to be, how do you add the butterfly?
Yeah.
There's gonna be in the one.
Actually, so, okay, let's go here. All right. How many spheres are there in each color? One sphere of each color. Okay? Then, figure eights. How many figure eights did we say they were? There's actually three, right? You got X, you got Y, then you got Z as well. Okay? This is only one of the butterflies. There are actually 5 butterflies. Okay? They're not all butterfly shaped, okay, just so you know. But when we start thinking about where they go, right? We said that it's trying to get as close as we can to the nucleus with staying as far away from other electrons as we can, right? So if we take these green figure eights, for example, right? If we have an electron that's on the x-axis figure eight, the farthest away from the x-axis figure eight you can get is the y-axis, right? Does that make sense? That's as far away from the x-axis as you can get. Yes? No? Maybe?
Yes.
Okay. And if you already have an electron in the x-axis and in the y-axis, the farthest you can get away from those two would be the z-axis, right? Does that make sense? That's spacing-wise, that's as far away from the other two as you can get. Okay? Now, the butterflies, right, start filling in the space. The first butterfly exists in between which two axes? X and Y. There's a butterfly that exists between X and Z. So it would kind of like come out towards you guys this way. Does that make sense? Right? There's actually 5 of them. And then there's another one, Y and Z. But then there's 2 more that don't follow that shape. They're just kind of weird, so I won't draw those for you. But the idea being that we're just sort of filling in the space. How close can we get to the nucleus while still staying away from the other electrons? Jules, go ahead. You will see that there is a pattern that shows up. That hopefully, if you understand the pattern, you won't have to memorize all of them. And that's where we're going to go today. We're going to start hitting the pattern. Okay. So also, actually that's a good transition, Jules, right? There's also, right, the first thing we drew was this, right? Okay? Yellow only has what? 1, and what shape is it? Sphere, right? Why does yellow only have one shape? It's the closest to the nucleus. In order to start seeing these other shapes, these electrons have to have room to sort of spread out a little bit. Does that make sense? The reason that there are no yellow figure 8s is because even if we put electrons here and here, even if we put electrons like here and here, they would still be too close to these electrons, so they won't go there. Does that make sense? So, as you see, right, every time we add a new color, we add a new shape, right? And then when we add blue, we add the butterfly, right? So new color, new shape, because we keep getting farther and farther away from the nucleus, now we have more room for those electrons to spread out so they can fill in the spaces of being close to the nucleus while still being away from other electrons. Does that make sense? Okay. Good so far. All right. Now let's start interpreting this drawing. Okay? All right. Back to your outline. Front page. So we talked about orbitals are areas that have high probability of finding electrons. What we want to do for the rest of today and maybe into tomorrow is talk about quantum numbers. And I think you guys wrote these down already, right? Okay. Yeah. Quantum numbers are like an address. Each one of those orbitals that we drew on the previous drawing, on our big elaborate picture, each one of those orbitals is a space that is likely to contain electrons, depending on how many electrons are there. Each one of those spaces, whether it's a sphere, whether it's a figure 8, whether it's a butterfly, whether it's yellow, red, blue, or green, each one of those spaces has its own unique combination of quantum numbers that distinguishes it from every other place around the atom. Or sorry, I should say around the nucleus. Okay? We said it's a lot like your address, right? Your house is a place. Are we guaranteed to find you there? No. Is it likely that you're there? Yeah, because you've been there a lot in the past, right? Your house has an address. It distinguishes your house from every other house there is. There are some similarities, right? But at the end of the day, there has to be something different about your address than every other address. Same thing with these quantum numbers. Every orbital has to have its own unique set of quantum numbers that is different from every other quantum number. Okay? Good there? All right. So let's start talking about those quantum numbers. On Wednesday, I believe, we started with principal quantum number. Is that correct? Yeah. Okay. So we said the principal quantum number, did we fill in the whole thing on principal quantum number? Okay. Principal quantum number. First, we used the lowercase letter n to represent the principal quantum number. And we said this starts talking to us about energy, or big areas, main energy levels. Remember, Bohr told us about energy levels, but Bohr's energy levels were rungs on a ladder, right? Here, 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 or here, and nowhere else. While that's not the case with Schrodinger's model, right? You guys can see Schrodinger's model up here, right? Yeah, okay. While there isn't blank areas, there are certain areas that are darker than other areas, right? And we said the farther we are, right, the darker areas relate to what? This dark area here, how are the electrons there different than this dark area? Higher energy, right? So the farther out we go, the more energy these electrons have. How did we represent this on our drawing? Do we remember? I think we talked about this on Wednesday, right? Have you guys make those deductive conclusion? Colors, right? Every time we change color, we go to a different principal quantum level. Okay? So, here's where eventually my drawing might be a little clearer than your drawing. Okay? So, this is the first orbital that we drew. It's the closest to the nucleus. It's the lowest energy. We represent that with a quantum number n equals 1. Okay? Next, we change colors. Right? So we said changing colors relates to a new principal energy level. Okay? But this principal energy level, because it's a little farther out from the nucleus, it has space for a few more electrons to fill in. Right? So we added these shapes. These 3 orbitals plus the 4th one, right, that we can't see, right? There's this 4th one that goes this way, yes? Right? All of them together are the second principal energy level. And any one of these red orbitals would have an n value equal to 2. So this red sphere, we would start off with n equals 2. Hold on. And then these figure 8s, right? I'm going to separate them. You'll see why as we move along. Okay? I'm going to put one over here. I'm going to put one over here. Right? This one's n would be equal to 2. And this one's n would be equal to 2 because they're all red. They're all in the same principal energy level. Hold on one second. Let me do the blues and then we'll go. Okay? All right. Then, right, we added this blue one, but then we added these blues and we added these blues. Right? All of these together, one sphere, 3 figure 8s. And do we remember how many butterflies there were? 5 butterflies, even though they all don't look like butterflies, right? All of these together are the 3rd principal energy level. Any one of these orbitals would have an n value equal to 3. Okay? So, this sphere, n equals 3. These 2 figure 8s. Again, I'll separate them. I'll put this one over here. I'll put this one over here. Both of them have n equals 3. But then this butterfly, because it's blue, also has n equals 3. Okay? Good so far? Okay. Questions that we still have, or did we clear those up as we went along? Ronnie, go ahead. The n represents, for simplicity's sake for our drawing, it represents the color of the orbital. Okay? If we go back to this picture of Schrodinger's model of the atom, Ronnie, each one of those n's would represent, like, see how, like, there's a dark area here, then there's the lighter area, then another dark area, then a lighter, then another dark area. Every time we go to the next dark area, that would be another n, another principal energy level. Okay? If we want to relate it back to the address idea, okay, n represents like a city. Okay? There's lots of places that there could be electrons in our city. But all of your addresses all have something in common. Westlake, Ohio, right? But there are lots of places within Westlake where we could have people living. There's lots of places in a principal energy level there could be electrons depending on its size. Okay? So that's where we're going to get to next. Jules, you good or no? Yep.
So first, like the second one, there'd be 4 because there's the
Yep. So Joe's question was, right, when we're looking at the total number of orbitals, in the second principal energy level, there are actually 4 orbitals, a sphere and 3 figure eights, right? In the third principal energy level, there are actually 9 orbitals. The sphere, 3 figure eights, and then 5 butterflies, okay? I don't have all 5 butterflies drawn there, obviously, because it gets really complex. But yes, if we're talking about actual number of orbitals, that's how we would count them, okay? All right, good there. Okay, I'm going to skip something on your outline. So, if you would please, flip to page 2 of your outline and find the Roman numeral number 5, that says the angular momentum quantum number. Okay? So, Jules, we just discussed that within principal energy levels, there may be several orbitals. Just like in Westlake, there's lots of houses, we have to distinguish all of them from each other. We start by doing that in the blue energy level, the third principal energy level, there are actually 9 orbitals. We got to distinguish them all from each other somehow. We start that with the angular momentum quantum number. First, we use like a script L or like a cursive L to represent that. It's actually L. I usually write mine as cursive to distinguish it from my I's and my 1's. So, okay, because I write my I's and my 1's all kind of the same. So, but more importantly, the angular momentum quantum number indicates the sublevel and the consequent shape of the orbital. Okay? And I believe you have this chart already written in your outline, right? L equals 0 for s orbital, L equals 1 for p orbital, L equals 2 for d orbital, L equals 3 for f orbital. Okay? I'll explain that off of your drawing. Okay? So, the angular momentum quantum number, lowercase l, and it tells us about the shape of the orbital. Okay? Do we have this written down? Okay. Let's transition back to our picture. And let's start, actually, if I have this up, can you guys still see? Can you see like this part? It's easier for me to flip slides if I have this thing on the side. Is it big enough for you guys to see? Is that okay? Yeah. All right. First one we drew was this one right here. Okay? And then we said every time we switch a color, what's the first thing that we draw? Sphere. Okay? Spheres we call, wish it would write properly. Spheres we call s orbitals. So this is an s orbital. And this, actually we'll go here. This is an s orbital. And this is an s orbital. All spheres are s orbitals. But they are different from each other in that they are in different principal energy levels. Okay? So how do I know whether I'm talking about the blue sphere or the red sphere or the yellow sphere? Well, we already started with our quantum numbers, right? We know that anything blue has n equals 3. The next quantum number I just told you was L. And if you look on your chart, any s orbital, its L value is 0. So this blue sphere, n equals 3, L equals 0. The red sphere is still a sphere, so its L value is 0. but its n value is 2. And then yellow sphere, because it's a sphere, L equals 0, but now it's different from the other ones because it has a different n value, or a principal quantum number. Okay? Good so far? Far good. Spheres are always zeros. Okay? But there are different shapes that we drew, right? For instance, these, right, are figure eights. Okay? Figure eights we refer to as p orbitals. Okay? These are p orbitals. These are p orbitals. And these are p orbitals. Any figure 8 is a p orbital. Ronnie, go ahead. Yes, we're not done with that yet. That's what the rest of this outline is about. Okay? But yeah, that could be definitely a fair question. Like, give me a similarity and a difference between red sphere and blue sphere. You know, like that could be a fair question, sure. All right. These p orbitals, we didn't label them before, but they're green. Green is the 4th principal energy level. Okay, n equals 4. But, sorry, I should do this. Separate them again. Ooh, not what I wanted. Here. We'll put this one down here. Put this one over here. Each of these, n equals 4, n equals 4. But because they're p orbitals, right? If you look on your sheet, how do we distinguish p orbitals, or how do we show p orbitals? L values are equal to 1. Okay? If we go up here, these are p orbitals. They're figure 8 shaped, but they're in the previous principal energy level. But because they're p orbitals, L equals 1. Okay? These are p orbitals. And that means L equals 1. Okay? Good there? Yes, that would be the same for the z-axis as well. Yeah. Okay? So that means the next quantum number, we have to decide how do we tell the difference between x, y, and z. That's where we're headed next. We're not there yet. Okay? All right. When we got to the blues, we added this one, right? The butterfly shape is a d orbital. Any butterfly shape is a d orbital. So that means this is a d orbital as well. Okay? And if you look at your chart on your outline, d orbitals have L values equal to 2. So this one, it's a d orbital. It gets an L value equal to 2, but its n value is 3. And this one has an L value of 2, but its n value is 4, because it's in the 4th energy level. Okay? Good with that so far? F, as we said, is even weirder shape, so I'm not going to draw that one. So I won't give you that one like on a test or anything, Devlin, but know that it does exist. Okay? Hold on. Wait. Whoa, freeze. Let me just wrap this up real quick. Okay? All right. So, hold on. Freeze. So, we said that the principal energy level sort of relates to a city. Okay? The angular momentum quantum number talks about the shape. If we relate it back to an address, that's kind of like a neighborhood within the city. All right? In Westlake, some of you live in Settlers, right? Some of you live in Musical Streets, and then some of you live in other neighborhoods around Westlake, right? You're all Westlake, but there's areas within Westlake where we're more likely to find people. Yes? Okay? That's what we're getting at here. Okay? So tomorrow, we'll talk about the next two quantum numbers. Okay? And we'll distinguish them from the other ones. No quiz tomorrow. We'll push the quiz back to Wednesday. Okay? And that means probably test is going to move to Monday. Probably. I'm not promising that. Okay? All right. We'll pick it up from there tomorrow.